My name is Shelbi Jenkins. I am an assistant professor at the University of Arizona in the Electrical and Computer Engineering department. And then my co-instructor is Wyatt Wallis. He's a PhD student that I've been working with for a couple of years. Um, our course is on quantum network integrated devices and systems. So we'll cover a pretty broad amount of material today, but we're going to try and keep it digestible, I guess is what we would call it. So quick overview of what we're going to be talking about. The first half of the course is going to be, like I said, pretty high level. We're going to talk about like introductions and motivations as to why we care about quantum networks and particularly photonic devices inside of quantum networks. We'll talk about the purpose of distributing EPR pairs across the quantum network and all of the different technologies that go into that. And then we'll just cover some basics of waveguides. We're hoping that this will be helpful, particularly if you are taking Marco Longcar's class tomorrow, which I suspect will be a little bit more intensive. But we'll get through all of that, sort of the upper level, high level material, and then we'll take a 15 to 20-minute break. And then the second half of the course will be a little bit more technical, a little bit more into the specifics of how you actually make these devices, what they're used for, how they work, and all sorts of things like that. Like we said, if you have any questions, please put them in the Q&A. Wyatt will be monitoring the Q&A session while I am speaking. If he needs to interrupt to ask any questions for me, feel free to do that, Wyatt. And then vice versa, when he is going, I will be addressing questions and comments in the chat. All right, without further ado, first, our sort of introduction of why do we care about quantum networks? There's a lot of really practical applications for quantum networks that can have a lot of impact in a lot of different industries, one of them being distributed quantum computing. So being able to have multiple quantum computers work in parallel with each other to solve the same sort of computational problems in the same time frame. In order to do that, you need to have a network that connects them and can share EPR pairs or entanglement across multiple quantum computers. So that's one application. Another one is clock synchronization between devices. Quantum enhanced sensing, which includes long baselines for telescopes. And then finally, secure communications. If you were there for Mike Raymer's intro class on Monday, one of the fundamentals of quantum mechanics is that you can't observe these entangled pairs without destroying them. So you can effectively have entirely secure communications just by nature of using entangled pairs to facilitate that communication between different consumer nodes or computers or whatever we want to call them. And for purposes of what we're going to talk about pretty soon, we'll call them consumer nodes, but what you call them depends on your applications ultimately in the end. So I'm sure this week a lot of people have talked about this source in the middle architecture. If you haven't, we'll just go over it very briefly. So at this top level system we have here, this is entanglement swapping, where theoretically what we want to have is Alice and Bob share an entangled pair together. One way that we can do that was we can have Alice generate an entangled pair at her node and then send it to this intermediate node where they perform a Bell state measurement. And then through those measurements, you perform entanglement swapping, which is not really covered in this class. It's covered in previous classes and probably some of the ones tomorrow. But then you can entanglement swap another pair and send the other half of that pair to Bob. So you can generate entanglement between Alice and Bob, but you have to have this intermediate node. So alternatively, what people are proposing is this source in the middle architecture where you have the intermediate node is what is actually generating the entangled photon pairs or EPR pairs, and then sending those pairs directly to Alice and Bob. This is useful because we can effectively cover twice the distance between Alice and Bob without having to do that intermediate step of entanglement swapping. So this is our kind of high level argument for having a source in the middle architecture where that source generates the EPR pairs and then distributes them along a network to our consumer pairs, which in this case is Alice and Bob. We can have more than one, and we will show at least one instance where we have, I think, maybe 20 consumer node pairs, but you'll need at least two. But theoretically, we want to be able to scale that up, a lot. And the way that we're going to propose doing this eventually is through making integrated devices. These integrated devices are very small, and so because they are small, you can make more of them in the same amount of space, or for the same amount of space as, say, like a fiber tabletop system. So this is our very high-level overview motivation for wanting to explore integrated devices for quantum networks. Yes, okay. So the first technical thing we're going to talk about is EPR-pair generation, which is kind of the first step, obviously, in being able to distribute entanglement across the network. We have two examples of how to generate EPR pairs. There's spontaneous parametric down conversion, which is a second-order nonlinear process, and there's four-wave mixing, which is a third-order nonlinear process. So for SPDC, we have an incoming pump signal of a certain wavelength or frequency, typically in the visible, and then it interacts with this nonlinear crystal. It can be a lot of different types of crystals depending on what kind of output you want and what kind of wavelengths you want to work with. But for each of these processes, what's going to happen is that this nonlinear process is going to generate a signal and an idler photon pair, where the frequencies of the signal and idler photon will add to be the same frequency as the pump frequency. So when these signal and idler photons exit from the crystal after this nonlinear process, they are entangled both in wavelength and polarization. And we'll use that information a little bit more later. The second process that we can potentially use is four-wave mixing, which is a third-order nonlinear effect where you have two incoming pump frequencies and two output signal and idler frequencies, such that the sum of the signal and idler frequency is equal to the sum of the two pump frequencies. Both of these processes are going to give you what here is called a joint spectrum, where this is the relationship between the signal and idler wavelengths, where you can see they are inversely related or anti-correlated. Both of them can be entangled in wavelength and polarization. And there are some trade-offs to doing either the second order SPDC or third order four-wave mixing. And depending on what you're trying to achieve and the limitations of your system will decide which ones or which process you're more likely to have success with. So we have this plot here. So like we said, one of them is second order, one of them is third order. When we talk about materials, second order nonlinear materials typically have to be crystalline structures, so they are not as common. Whereas every material that you can work with optically will have some third order nonlinear constant. So if you have a high enough power, you can achieve that third order effect always, where you cannot always achieve it with every type of material for second order. Additionally, when we're talking about fabricating devices out of these, the materials for second order tend to be more, since they're crystalline, they're not very malleable, they're harder to fabricate, they don't adhere very well. But if you can use any type of material, fabricating with them becomes a lot easier. Like I said, both of these can be polarization and wavelengths, or can generate polarization and wavelength entanglement between the photon pairs. And then phase matching, which we didn't really talk about because we're trying to keep this, we don't want to go deep into E&M theory with you guys because we don't think that would be as helpful as giving you the end result. But phase matching is essentially what determines how well your nonlinear process is working or how effective it is. And so being able to phase match for Chi2 materials or second order materials is a lot more difficult. You have to be a lot more precise. So getting that output, that SPDC output that you're looking for is a lot more difficult versus with third order, the phase matching is very easy and can be done over a very long distance. So getting that process to work is a lot simpler. And then when we talked earlier about how that SPDC source has one input frequency and it has to be in the visible spectrum, But when we work with four-wave mixing, you can potentially have your incoming and output frequencies both in the IR spectrum. And this is helpful because when you're fabricating devices, most of them are going to be wavelength dependent, typically only over a very small range. So having photonic devices that can work in the visible and the IR is really complicated. So if you can potentially do four-wave mixing, which you can a lot of the time, but it's easier to fabricate devices that can work for four-wave mixing because you don't have to work across different spectrums or large spectrums of the like you don't have to work across visible and the IR or like the O-band, S-band. You can just have one that works. You can have all of your frequencies within the same band. And then finally, the main appeal for SPDC over four-wave mixing is that it does generate higher rates of entangled photon pairs because it is second order. And second order effects produce higher intensity outputs. So that is definitely a trade-off when looking at four-wave mixing versus SPDC. But like I said, this all just comes down to what kind of system you're looking at, what kinds of limitations you have when it comes to fabrication or materials, or how high of an output you actually need from your EPR-pair generation. Yeah, so this is just, these are common trade-offs between the two types. Which one you're going to want to choose depends on your situation. But these are what are seen as the best options, you know, or the two most common options for photonic devices. Okay, I guess we're going to do our first Zoom poll. Like I said, should be, well, we'll just read it. Okay, so in spontaneous parametric down conversion, or SPDC, which statement best describes the energy conservation? The signal photon always has higher energy than the pump. The pump photon splits between two photons whose total energy equals the pump energy. The energy is not conserved due to quantum fluctuations, or the either photons carry all the energy in the pump. Yeah, so most of you got it perfectly correct. The pump photon splits where that total energy equals the pump energy. This is the same thing as we said before, where the frequency of the signal in idler will add to the same frequency as the pump photon, or the pump signal, pump frequency. Okay, so moving on. Here, moving on to a bigger system in our, you know, quantum networks. When we talk about generating EPR pairs, but another thing that we want to do is herald our EPR pairs, which is essentially a method of us confirming that the photon pairs in our network are entangled, and it gives us some level of information about them so that we can use them and manipulate them in a way that is useful for us without destroying that entanglement. So how we're going to do this is by having this EPR pair generator or part of a source node where we have two SPDC sources. So this output spectrum from both of these SPDC sources will be this Gaussian distribution. So this wavelength, or these wavelengths channel or span about 180 different channels of different wavelengths, but the number of photons in them varies with this Gaussian distribution. So what we do is we have our two SPDC sources where, let's say, if they both output EPR pairs at the same time, we mix them on this 50-50 beam splitter, which is this black box right here. So now it is indistinguishable which photon is coming from which arm of this, or which SPDC source. So theoretically, if we send this through this DMUX, which has all of these 180 channels in it, if on both arms we get the same wavelength detected at the same time, then we can backtrack because we know that there is a relationship between the wavelengths of our signal and idler photons. That will be true of both of these as well. So if our idler photons are of the same wavelength, we know that our signal photons will be the same wavelength as well. So from this, using that relationship of pump frequency is equal to the sum of signal and idler frequency, we can determine the signal frequencies by detecting the frequency of the idler. So that gives us information about the wavelength of our signal photons, which is, as I discussed earlier, a degree of entanglement. And since we've measured it, that degree of entanglement is now gone. We've done that measurement. We've, collapsed that wave function, or however you want to see it. But earlier we discussed that there is also a degree of polarization entanglement. And so what's happening with this beam splitter here, there's something called Hong-O-Mandel interference or HOM interference. And this says that if you have two incoming photons that are completely indistinguishable, meaning they are the same wavelength, the same polarization, and they interfere at the same time, they will always exit one side or the other, both of them. Whereas if you have some distinguishability between them, there's a chance that you can get one on one side and one on the other. So since we said earlier that we are getting the same wavelength detection click at the same time in two different arms, we must conclude that there is some degree of distinguishability between them, which we conclude to be polarization. So now we know that they have opposite polarizations, but we don't know which one is which. So this is how we can maintain entanglement between our signal and signal photons that are now being sent into the network and onto consumer nodes without actually knowing what the polarization is of each photon, because then otherwise we wouldn't be able to use the entanglement. So I know that was a little wordy, but this is just here to show you that we can, in our source node, confirm that we have entanglement between two signal photons in our network. We can know where they are in the network, and we have their wavelength or frequency information, which is important when you want to couple into quantum memories. You want to know the correct wavelength so that you convert from the infrared into the visible, because quantum memories are not compatible with infrared light. They're largely compatible with visible light. So that's why we want to have the wavelength information. But okay, so once we have heralded our EPR pairs, then we can send them on into the network and try and satisfy what we call consumer node requests. So our basic design for a network is we have a quantum transmitter or a source node, and this has an EPR generation. It does the Bell state measurement. We can have a mode converter in there theoretically to change it to visible before we transmit it. Or alternatively, we can transmit that photon to the quantum receiver or consumer node, where it can do that mode conversion right before the memory. And then we will also have quantum memories in the receiver node to actually store that entanglement and be able to source it out later. This is just a more technical version of what our nodes look like. So our source node has the same EPR pair generator and Bell state measurement. For some work that we've done previously, we've assumed that our source node is also a consumer node. So it also has this mode converter and quantum memory, along with these wavelength selective switches. And these WSSs are one of those key photonic devices that we're going to want to be able to integrate and implement later, because that is what is allowing us to redirect which photons are going to which consumer nodes. So this right here is just a source node. We also have multiple consumer nodes that only consist of a mode converter and a quantum memory, where an incoming photon can either be directed into a quantum memory or it can be redirected to a different consumer node. So those are two types of nodes. There's a little bit of overlap between them, but for purposes of what we're going to talk about today, for any network, there's only one source node that generates EPR pairs sent into the network. The rest of them will be consumer nodes. Okay, our Zoom poll question 2. So what we just talked about in our proposed network, which systems cannot be included in your source node? This is solely based on the assumptions that we talked about for systems that we've shown today. All right, so this was a little bit of a trick question. Not really. The answer is that you can actually have all of these in the source node if you would like. The tricky part about having a mode converter in the source node is that you then have to have transmission links that can work in the visible, which is a little bit more difficult, but there is potential, or there are potential benefits of having that in there. The quantum memory can be in the source node because, like we said, it is also considered a consumer node for what we're doing here. And then the EPR generator and the Bell state measurement are what give us that heralding. And then finally, the wavelength selective switches allow us to decide which photons are going where. So when we talk about the links between source nodes and consumer nodes, or consumer nodes and other consumer nodes, there are a couple considerations we want to account for. This can be done in free space, fiber, or via integrated circuits. It just depends on, like I said, these different considerations. One of them is transmission loss. When you're working with individual photons, loss is going to be pretty detrimental. We want to be able to keep as many photons as we can. So things like fiber and integrated devices are going to be a lot more lossy than free space. In addition, polarization considerations. Like I said, theoretically, we're working with entanglement in the degree of polarization. So when you're working with regular optical fiber, if it's not polarization maintaining, you can lose that polarization state, which then effectively makes it useless in the context of our quantum network. And so for this reason, like again, free space might be a little bit simpler when it comes to maintaining polarization, or just using polarization maintaining fiber, which also has higher transmission loss. And then the last thing that we want to consider is path manipulation, because like I've said, we've been talking about routing these photons to different consumer nodes across the network and rerouting them and reconfiguring them. So being able to change the path quickly and easily is going to be pretty essential when you're looking at large scale networks. So for those reasons, free space might not be as great, and it won't be as great actually. So for when it comes to path manipulation, using integrated devices or other waveguide materials such as fiber is going to be really, really helpful in that regard. Yeah, and then we'll talk very, very briefly about some further polarization considerations when we get closer into like waveguide basics. But the other thing that we want to consider is routing. So like we said, we have this Gaussian spectrum output from our SPDC sources, where we can assume that we have at our peak, we've got about 4,000 EPR pairs for the peak channels, maybe a little bit more, 4,500 perhaps. But we want to be able to route these to different parts of the network depending on which consumer nodes are requesting EPR pairs. We want to make it so that if, like, let's say there's a quantum computer at, consumer nodes A, B, and C, if quantum computer A needs 10 times more entangled pairs than quantum computer C, we want to make sure that we can accommodate that. So we want to have something that is reconfigurable. So that's why we have these WDMs, wavelength division multiplexing, where we can split out that signal into these 180-ish different channels. But we also want to use the wavelength selective switches to be able to route them to different places depending on our consumer demands. And so this is another example of a device that would ideally be made into integrated circuits to be able to scale them. Wyatt will talk more about this in depth, but one example would be ring resonators can act as filters to direct certain wavelengths to certain different waveguides. And then if you wanted to use either electro-optic or thermo-optic, if you wanted to affect them electrically or thermo-optically, then you can change which wavelengths those filters are filtering out. So you can change which wavelengths will be directed where. So this is what we mean when we talk about reconfigurability. So just going forward, when we talk about photonic devices, these are the kind of things that we want you to keep in mind as to why we are talking about this. Yeah, okay. Zoom poll question 3. Compared to free space propagation, waveguides primarily offer higher speeds of light, no losses, infinite bandwidth, or reduced diffraction and controlled propagation. All right, looks like Almost everybody got it. You're right. We reduce the diffraction. This controlled propagation is what I was talking about. When we talk about routing, being able to actually physically control where the light is going is a lot simpler in a fiber than free space. So this is the benefit of using them. Okay, and then really quickly, we're going to go through, this is some work that we've done actually modeling quantum networks and how to distribute EPR pairs across the network. So here we have what we call a toy network, where we have source node A, which is also a consumer node, and then we have consumer nodes B through F. So let's say all of these consumer nodes are requesting pairs, and we want to effectively get a fair amount of EPR pairs across the consumer nodes. So there's two things that we look at here. One of them is we look at the routing, so how much loss you can get from following different routes, and then we look at spectrum allocation. So when we look at routes, one thing that we need to consider is what we call link disjoint. So for instance, let's say we want to entangle nodes E and D. We can send one signal of this wavelength. I say green, they're all in the IR, but we're going to say green for simplicity. One can go from A to F to E, while the other one can go A to B to C to D. And then we have distributed entanglement across nodes D and E. Same thing, if we want to entangle C and F, we can send one directly to F and one through B to C. One thing that we cannot do, because currently we are considering static networks, is we cannot send two wavelengths of the same, or two photons of the same wavelength along the same line and say have one go to F and one redirect through F. That's because we cannot distinguish between those wavelength channels. We can't distinguish between which of those photons in that channel will go to F and which will go to E. They have to either go all or none. So if we wanted to entangle F and E, what we would have to do is we would have to send one through F, or one directly to F and one from A, maybe from to B to E, or all the way down B to C to E, B to C to D to E, whichever one makes sense. So when we look at the routing, what we did is we looked at all of these consumer pairs, all of the potential paths that a photon could take to get all of the consumer nodes, and we looked at how much loss you would get. For this, we were assuming 0.4 dBm per kilometer, and I want to say each of these links in this toy network are between 5 and 10 kilometers. And then each WSS will lose either 4 or 8 dB per WSS. We looked at it for both, just because that is when you look at commercial WSSs in the market, that is the range of loss that we see for all of them. So we went through and we mapped all of these potential paths and all of their loss. And then we looked at spectrum allocation. So what this is saying that for this Gaussian distribution, each of these channels has a different number of photons emitted from the source node. So for instance, these middle channels will have 4,500, whereas the ones at the ends will only have about 500. So what we did is we wanted to map the channel sizes with that loss per path that we're seeing. And what we wanted to do, we did 2 units of measurement. One of them was looking at, we were trying to maximize the minimum number of EPR pairs that every single consumer node received. And the other one was looking at the Jane index, which in resource allocation is a standardized unit or measurement of fairness across the network. So we did this for a couple of networks. Right now, we're only going to look at this Manhattan incumbent local exchange carrier network. So this is an actual network that exists in Manhattan. It's multiple source nodes connected, or multiple nodes connected through fiber. We only have their geographical location and their coordinates. We don't have the actual paths that they are taking. So we did this as like bird's eye view distance, when in reality, they will be a little bit longer. But so what we did is we assumed all of these nodes, or all of these different nodes, and we placed our source node at all of these different nodes to see which ones perform better. We have a couple of different algorithms. Most of them are just simple algorithms for resource allocation. Some of them are from computation assignments for different computer processes. And so we, like I said, we looked at these 2 things. One of them is the minimum EPR pair rate for all of these for all of our nodes. We did it again for 4 dB and 8 dB. And for this, we see that node M performs way better than all of the other ones. And this is because node M is the only node in this network that is connected to every single other node. So naturally, it can outperform all the other ones because it has easier access to all of the other consumer nodes. Alternatively, P and Q have the least connections to any of the other nodes. I think they are both only connected to 2 or 4. And then we look at Jane index. We see that when it comes to source node location, it doesn't matter as much if you want to get like this measure of fairness through the Jane index until you get out to these nodes P and Q. And again, this is because they are not very well connected to all the other ones. Yeah, so this is just our example of showing you how quantum networks can be integrated into existing fiber networks so that we don't have to, theoretically down the line, we won't have to entirely redo all of the infrastructure needed to house quantum networks. We can just put them into existing fiber networks. And the way that we'll do that is through different integrated devices, which Wyatt will talk more in depth on later. Okay, now we're just gonna very quickly, we'll go through some waveguide basics. If you already know this, great. This, like I said, it's pretty high level overview. We're not gonna do any of the derivations from like Maxwell's equations. So some of this, I will give you the solution and you'll just have to trust me. But we just wanted to make this like a little more digestible. So when we talk about the first thing about waveguides is that this is going to be our general structure. So we have something of material N1 surrounded by materials N3 and N2. A lot of the time, N3 and N2 will be the same. So it'll be symmetric on the top and bottom. Sometimes it won't be. What needs to be true is that this material that we're trying to propagate the light in needs to be of a higher refractive index. And that is because of Snell's law here. So Snell's law is just what defines how light will be refracted or reflected through different materials. And there's this thing called the critical angle here that says that if you come in at a certain angle, that because of this angle depends on the difference between N1 and N2 or N1 and N3, depending on which surface or which interface you're looking at. But it says that for this critical angle, 100% of the light will be reflected. And so if you can input your light into this waveguide at that critical angle, it will just continue to reflect off the sides and propagate along the waveguide. That's how we can manipulate the path and redirect it where we want to go using these waveguides. That's why they're called waveguides. Yeah. So one of the defining characteristics of a waveguide is called the effective index. The effective index is calculated, like I said, again, we're not going to do the derivation, but it's related to the index of your core, your cladding or your outside material, the dimensions of your waveguide, the symmetry. But it essentially gives, when we say this effective index, this gives us information about our propagation constant. Our propagation constant tells us how the light is going to propagate through the waveguide and what speed it will propagate. The other thing that the effective index tells us is which modes will be supported. So these are examples of different modes, TE and TM modes. So this is like this is the first order mode where you can see most of it. This is the N2 material. This is N1, N3, N2. But we can see most of the light here is confined within the mode. There's one peak. For the second order mode, which is M1, confusing enough, we still have that sort of, there are arms here that are not confined within the core of the material, but this is just to say you can have higher and higher modes propagate if you have geometry and materials that support that. This what we call here is the confinement factor. It tells you how much of the mode is confined to the core. And depending on what you're doing, you're going to want to have more or less confinement to your actual core material versus having it in your cladding material. I think for most of the things that we will talk about today, having good confinement or high confinement to the core is going to be preferable, but for people who are working in different material claddings, it might be beneficial to have more of the light interact with that, with the cladding rather than the core. So, yeah. So these are the modes that are able to propagate for certain waveguide geometries. And a mode is just an electromagnetic field distribution. Certain field distributions will be allowed within certain geometries and certain ones will not. They just will not physically be possible, or they won't be able to propagate. But yeah, like I said, this is all determined by the effective index and the geometry of your waveguides. And then I forgot the K vector is just the direction that you're propagating through a wave. So if we send in light this direction, the K vector will be pointing to the right. Yeah, that's right. Yeah. Okay, so this is what we call a BV diagram. Again, we're not going to go through the derivation for this because you end up with some intrinsic equations. But what this plot is telling us here is that for certain waveguide geometries, these are different allowable modes, M1 or M0, M1, M2. And this is saying that once you hit certain value of V, which is determined by, again, your geometry, your materials, then you can start to increase the number of modes or the number of field distributions that are allowed within your waveguides. Theoretically, if you have a perfectly symmetric waveguide, you can get this V down to 0, which is effectively having 0 core material. But when we talk about fiber, a lot of the time we're going to be talking about single mode fiber. So that's fiber that only supports this first mode, not any of the others. If you want to work with multi-mode fiber, there are some applications for that. Typically, it's not considered for long distance communications because we'll talk about dispersion, but modal dispersion where different modes will travel at different speeds. So that can end up jumbling a lot of your signal, getting it spreads out and mixes with others, makes it really hard to distinguish. So for long distance, we prefer to work with just single mode because that will propagate at one speed. So you know when exactly it's going to show up at the other end. Okay, another Zoom poll. Why must the refractive index of the core be higher than that of the cladding? All right, for those of you that said B, that is correct. The difference between the core index and the cladding index is what allows us to achieve that critical angle total internal reflection. If you have it say the opposite, where it's the core material is less than the cladding material, then you won't see that critical coupling. You'll just have it refract into the cladding material and there won't be any waveguiding at all. Yes, all right. Okay, so we have a couple of considerations when we talk about waveguide loss. So one of them is coupling loss. Even if you are working with integrated devices where things are directly coupled into each other, getting a perfect match between the output from your laser or whatever your light source is into your waveguide there's going to be some mismatch. And so you're going to lose some light just in trying to get it into the waveguide itself. So that's our coupling loss. That's also true if you're just working with fibers. When we talked about our network with our WSSs, where there's 4 to 8 dB loss, a lot of that is going to be coupling loss. It's generally a very inefficient process, especially if you want to do switching where you have to move between different waveguides. There are ways to minimize coupling loss. You can do like index matching fluid. That's one option, but generally it's just accepted that you're going to see some loss, typically on the order of 3 to 6 dB for coupling. There's absorption loss. This is just inherent to all materials. unless you are working in a vacuum, some of your light is going to be absorbed into the material. This will be dissipated as heat. For the most part, it's not going to be a lot of heat, but for some things it can be, especially like if you're working with visible in silicon that absorbs a lot, so it can heat up, which depending on what you're working with, you might want to take that into consideration. A lot of the time it's going to be fine, but worth taking, it's worth considering. And then radiation, one of these examples is when we talk about bend loss. So if you take a fiber, if it's straight, it's it's going to have some loss per distance, but if you bend it, you're going to end up with a lot more loss. And what that is, shown here on the side, the light will essentially just evanescently couple out, which Wyatt will talk a little bit more about evanescence and what that means. But effectively, anytime that you have any bends in your fiber or in your waveguides that you've fabricated in an integrated circuit, any bend is going to produce some sort of loss more than just having a straight waveguide. And then finally, there's scattering. So there's two types of scattering. There's Rayleigh scattering, which is for things that are much, much smaller than the wavelength of your light. And then there's MIE scattering, which is for things on the order of or larger than your wavelength. So these would be things like defects. If you have any material dopants in there that are larger than your wavelength, you'll see a lot of scattering from that as well. And then I think the final thing we're going to talk about when it comes to waveguides is polarization and dispersion. So polarization, we talked about it. I didn't explain it yet. I'm going to do that now. Polarization is what is describing the oscillation of the electric field of your light. So that can be in a lot of different states. It can be linear, it can be circular, it can be in between, which is elliptical, or it can be unpolarized. For instance, the light that we get from the sun is unpolarized. Most of the light that you'll get out of a laser is going to be linearly polarized. And depending on the geometry of your waveguides, it will probably favor some type of polarization, usually horizontal or linearly polarized light. And this is dependent on your geometry. If you have a perfectly symmetric waveguide, they should be supported equally. This isn't in practice always the case, but theoretically that is how it should be. And then we have something called dispersion. And dispersion is where it determines how fast your light is going to travel within a medium. So when we talk about chromatic dispersion, that is the most, when people say dispersion, that's typically what they're referring to, where shorter wavelengths will travel faster or slower, depending on if there's dispersion. There's regular fiber, which has regular dispersion, and there's dispersion compensating fiber, which is the opposite. So different wavelengths are going to travel at different speeds. You can also, for different types of devices, you can have birefringence, which is where one axis will have a different index of refraction than the other axis. So you can have polarization dispersion, where one of them will be favored on one axis than the other, and they will propagate at different speeds. And then there's also modal dispersion. So we talked about how, depending on the characteristics of your waveguide, you can support one or more modes. And like I said earlier, when working with long haul networks, having multiple modes within a fiber can decrease or can degrade the quality of your signal because those modes are going to propagate at different speeds. So when you're working in fiber or any type of waveguide, you're going to want to consider how long of interaction you have with your materials and your devices, and whether or not you're going to need to compensate for these different types of dispersion, so that on the receiving end, of the consumer node of your network, you are getting the signal that you are anticipating. Yeah. And then I think, okay, we have one more Zoom poll question. What type of dispersion arises when different field distributions travel at different speeds? Yeah. So the answer for this one was C. I said it, I didn't write it down, so it's a little tricky, but I did specify earlier that a mode is an EM field, an electromagnetic field distribution that is allowed within a waveguide. So That's why we call it modal dispersion. Um, thank you. And then I think with that, yeah, this says 15-minute break, but I think we went a little bit quick. So I'm thinking maybe we take a 20-minute break and come back at 2:10 Arizona time, 4:10 Eastern time. I think that's correct. Somebody stop me if that's not correct. But yeah, and then with that, Wyatt will take over and we'll get into some of the nitty-gritty of actually fabricating these devices and what we can do with them.
Alrighty, welcome back, everybody. Thanks for attending. So, after that first half, which gave us a bit more of a macroscopic viewpoint on the network side of things, now let's dive down into the actual device, to the actual materials and device levels, and look at how we fabricate each of these devices, and then grow that into uh, how we can then manipulate quantum states and such. A little bit at the end. So the first thing here is what types of materials do we mainly work with? So a lot of the things that we're going to talk about today, the materials and then going on to the fabrication sorts of things, they're going to be kind of broad swaths. And so I'm not going to go too much into the specifics. And so these are going to be kind of generalizations, and there will be some overlap. So when I might say you would want to use this deposition process or this process, there are examples that would contradict that. And so that really depends on what you're working with, and especially if it's a novel material, it might be something completely different. But I'm just throwing that out there to begin with. This is going to be a very general overview. So the types of materials that we work with when we try to make these photonic integrated circuits, so waveguides, like we talked about, would be things like glass. So mainly fused silica would be one of the main ones, SiO2. There are some other ideas, or there are some other examples of that. Like you can dope glasses with different things, or you can give it a different base than silicon. So things like a chalcogenide glasses, those exist. So selenides, tellurides, things like that. Um, and else than that, you can dope them with various things. So you put little dopants in them, and it changes the overall optical properties. Now, how you can deposit those. Now, these deposition processes we'll cover more in depth later. Um, you can do things like chemical vapor depositions and sputtering mainly. Um, and then what's the usual benefits of glass is that it's usually a higher index. And by higher index, I mean about a 1.5 to 1.8 index. Then you go down to a polymer. Now remember, polymers are more so where you have these of long chains of atoms, either carbon or otherwise, and it can be an organic polymer. For instance, PMMA is used a lot, or it can be an inorganic polymer. Like there is some research going on now with sulfur polymers. And usually, when you get a polymer, not all the time, but usually, uh, a lot of materials are given to you in some sort of solvent, so it's given to you in a liquid state. And so when you do that, you're going to do what's called spin coating, which we'll cover here in a little bit. And the usual benefits of those polymers, some of them can have some higher refractive indexes, but but for the most part, they are around 1.4, 1.5. So they're a little bit lower, unfortunately. But what they do have is that they react to temperature changes a lot more. So there's a higher thermal optic coefficient. And that will really help when you're trying to work with Chi3 materials specifically. And then the last one I'm going to talk about on the slide is called SOI, or silicon on insulator. And so what that really is that you have a layer of silica, so SiO2, and it'll be in between, pretty much sandwiched between two layers of silicon. And so, you'll have what is it called? And so because of that, you'll be able to take full advantage of all the properties of silicon, because silicon has an index of 3 about, and this is all at 1550 nanometers. So silicon, because it has such a high index of refraction, it allows you to make very dense uh, devices and very dense architectures, and small waveguides. And so when you're able to do that, right, you're able to fit a lot more on there. We'll talk a bit more about that later, but yeah. And as you can see, the box is blank when it comes to the deposition process, and that's because there are several different ways that you can make these. For instance, one of them is you go through a process that essentially oxidizes a chunk of a larger portion of silicon. Um, And then that chunk that's oxidized is slowly thermally annealed, which then leaves one oxide layer in the middle between two silicon layers. There's also, I believe it's called epitaxy, which is a way in which you essentially grow crystalline silicon on top of another layer. So there's several different ways to do that. And so we're not really going to be covering some of those ways, especially the crystal growing uh, processes. So I just left that blank. And then moving on, so another type of material that we cover a lot and is, or that we talk about a lot, that's in the conversation a lot, is thin film lithium niobate. Now I have a diagram right here of that molecule. The green should be lithium. And if you look at this, each of these molecules are set up in a crystalline fashion, but but you can see that there's a somewhat of an order to them. And so that is why this is a really good active source for SPDC. You see, when they are not symmetric molecules, that lends itself to a very large or a larger second order response. And so that's really where the second order response comes from, is that there's a polarization or there's an inherent polarization in the molecule. It also helps that this material has a really good electro-optic response. It also helps that it has a refractive index of about 2.2 at telecom lengths, and that lends to it having very good mode confinement. And just like anything else that has large refractive index, you can make very small structures with it, and you can make very densely packed structures. And so because of that, it's a very good candidate for a lot of almost any, a lot of photonic architectures. Um, and so if you ever find yourself in the lab and you hear the word piplin or PPLN, that is referring to what's called periodically pulled lithium niobate. And so it's using these exact properties to its benefit, in which you essentially are applying an external electric field up, then down, then up, then down. So it periodically pulls um, the uh, the crystal, and so when you put an incident light through it, that allows that second order process to really take hold and generate your EPR pairs. So moving on, so once you picked out your material, now you need to decide, okay, what geometry am I going to use? How am I going to do this? So there's several different types of waveguides you can make. One of them would be I'm going to quickly run through these, but the most basic one is just a planar waveguide. I have some sort of substrate and I just have my desired film, and I'm just going to put light through the film, you know. Then there's the channel waveguide, where now we're saying, okay, well, we're not going to make it kind of a one-dimensional, we're going to make it a two-dimensional waveguide, where now there's where it's essentially a thin channel right there. Okay. Um, but there's the what's it called? There's the waveguide where you etch in and kind of make a trench, and then you fill in the trench with your material. That would be a good idea if, let's say, you're going to put a top cladding on it, but you're going to keep it thin because let's say you want another waveguide on top and you want to couple it into that guy on top of your first waveguide. So that's something to think about. And we're going to cover coupling in a couple slides here. Then we have rib or ridge waveguides, and so that would be for maybe there's an adhesion problem with your material, so you need more of that bulk material on the sides to help you out. And then lastly, we have this last one here where um, the problem with the rib and ridge waveguides is that if we were to show you the mode profile, it wouldn't look like a nice concentric circle. If we showed you the fundamental mode, you'd see it kind of balloon out at the bottom. And that's one of the main issues with the ribbon ridge waveguide sometimes, or a lot of the times, is that that mode profile shows you that it's going to be losing light to that ridge. So you want to be careful of that. And that's where with the last one, if you were able to choose, okay, I'm going to have a ridge of this material, and then my real waveguide, my real core is going to be this other material with an even higher refractive index, that will allow you to then control um, that mode profile and how much you want it to lose and control the loss to a much more palatable degree, perhaps. And then the last one I kind of skipped over is fiber. And so most of the time when it comes to fibers, they're fabricated a little bit differently than how we're going to show you integrated waveguides, right? Usually they're drawn, and usually they have a cylindrical, circular profile, and they have a cylindrical shape. And that's why we kind of have air, and then we have some sort of cladding, and then we have our internal core. All right. And then lastly, we have hollow core fibers. So these hollow core fibers, they have a lot of the same properties as normal fibers. It's a very the same general shape. The only thing though is that this one specifically is using this inner and outer tube geometry, and so it is fairly complicated. It's a much more complicated process. We won't be covering that here, but it's a more complicated process. And the main idea though is that if we go back to our ideas of total internal reflection, everything like that, that still applies here. And if we were to run through the very complicated calculations with Maxwell's equations and the boundary conditions, we would still get results, and which means that light still guides through this, but it's interacting with much less material, which is a good thing. Because in this case, since it's interacting with much less material, there's way less absorption. And if you're trying to preserve, let's say, uh, let's say you're trying to preserve a pump and you're trying to not have nonlinear things happen. Well, this would be a good candidate for that because, like I said, there's less interaction between the light and the material. So less nonlinearities, less but also less loss. Now, down there at the bottom, the big problem is though, is that there's more bend loss. So if you take one of these, if you take these hollow core fibers and you keep bending it around, then you will start to lose, you'll lose more of that information. You don't want that to happen. So that's where when you're making that decision between do you put in the cost for the hollow core fiber or the normal fiber, you ought to consider those things. So what materials go into these things? When it comes to normal fiber, it's most of the glasses that you've seen above, as well as some of the usual glasses you might even see in there are examples of some usual examples you'd see, or sorry, there are examples of some of the usual glasses you'd see in some more bulk optics. So like some of the glasses you'd see in some of the silicates and stuff like that you'd see in prisms and stuff like that. Hollow core fibers usually are the same as the solid core fibers. The usual candidate is usually SiO2 and stuff like that, but there are many other examples. Um, and here at the bottom, the last technology I have up here, because this is another architecture we're not going to cover too much here, but it does exist, is crystalline. So that is referring to a photonic crystal. And so you with these, you can make it with almost any material you'd make waveguides out of. So many different types of classes, many different types of polymers. And so because of that, the film deposition could be really any of them. The main benefit of those and what a photonic crystal really is think of these small nano pillars. So like think of like a cylindrical pillar coming out of your substrate. And think of just a grid of them. Maybe they're in a hexagonal pattern, maybe they're in a square pattern. But the point is that it's set up like how you would expect a crystal lattice to be set up. And you would see almost like a trench or a place where there's not these pillars. And that still has, if you can imagine, still has solutions to these Maxwell's equations. So it still guides light. However, it is very frequency dependent. And so these uh, these photonic crystal structures are very good for specific applications with specific when you want specific things to be done to specific wavelengths. Um, and also a neat thing about them is that because it's made out of all these small pillars, if you want interesting things to happen, like changing, you want to make certain logic happen in it in certain computing applications, then you can do things like adding another pillar that say, oh my goodness, what was it? One of them, I read a paper that had like zirconium oxide or something like that, some sort of dopant. So now you've changed the properties of this lattice. So it's a neat technology, but it's a little bit above what we're doing. So, you know, so now going into the fabrication. You've picked your material, you've picked what type of waveguide you want to make. Now we want to make it. So the diagram I have here is actually from a poster that I've made. And it goes through kind of the basic idea of your of a photolithography process, specifically a maskless photolithography process. We'll talk more about that. But the whole idea is that you spin coat on this orange material. That's the material you want to make a waveguide out of. And you're going to put that on top of a wafer. Usually it's going to be a silicon with a thin film of silicon dioxide on it or a few silica on it. All right. And that's so that way you get that total internal reflection. Then you want to deposit what's called a photoresist on top. That's usually also done by spin coating. And we'll talk more about that in a second. And usually these photoresists um, are they're usually organic polymers or other organic polymers that are able to that react to UV light when they're illuminated. And so what you're going to do when you do specifically maskless lithography here is that you're going to put it in this piece of equipment, whatever it is, and you're going to allow that equipment to basically write onto the photoresist layer whatever your pattern is. Maybe it's straight waveguides, maybe it's some of these other devices we're going to talk about. Um, and so what it does is that essentially these organic species start to change. Sometimes there is a certain acid inside of them that initiates. It's called a photo acid initiator and things like that. I'm not going to go too much into the chemistry. The point is that part of it reacts, part of it doesn't. And depending on what type of photoresist you have, you would then take it out of the machine and develop it in a different compound. And when it develops, it either uh, takes off the stuff that was reacted with, or the stuff that didn't react with the UV light. And then that leaves your pattern. All right. Then after that, you run it through an etching process, and we'll talk more about that. And then that gets rid of all that orange that's underneath that's exposed. And that's a good thing because now you have under your photoresist layer, you have the correct pattern on the film on the material you want. Then you just remove the photoresist. You can do that in a number of ways. It depends on which one you have. And then you add a top cladding onto it. Usually why we add top cladding instead of leaving in air is one of the most obvious things is environmental stuff. You know, if it touches anything else, it could ruin the waveguide. Um, if there's dust in the room in your lab at all, well then that's going to get in the way of your measurements and things like that. And also, if you wanted to put things like these phase shifters we've talked about, electrodes, thermal optic plates, anything like that, you should probably give the entire sample a flat top to work on. So you'd want to put it in a top cladding, which is usually of a low index. Um, so then from here, where do we do these fabrications in? What room do we go to? So we go to a clean room, right? And so the whole idea of a clean room, the big goal is how do we minimize dust, dirt, anything from the outside? And so usually that's where there's an immense amount of PPE that you're required to have, gown, gloves, etc. Sometimes some of them require you to have masks on. You got to have boots on, no dirt allowed. Um, and so these would be the types of places where all the equipment is stored, being where all these deposition processes are and things like that. Um, and so when you're trying to make these devices, it'd be a good idea to speak to whatever your clean room manager is and discuss what equipment you have in order to figure out what materials you can use. So know where these things are made, know what's in them, because I'm going to show you several different processes, and maybe in your own home institution, you might say, well, I want to make something with that material. But then when you look at your clean room, you realize I don't have this deposition process. I can't make that. So now you got to go back to the drawing board. Um, so going into material deposition, there's going to be three main types we're going to talk about today, and there's many different variations on some of these. So we're going to talk about an overarching theme. First one will be spin coating, going to be the easiest. Then we're going to talk about chemical vapor deposition or CVD. That's going to take the longest, but and is pretty expensive, but it has good results, of course. And then there's sputtering, which um, which is similar to CVD, but a little bit different. So when it comes to spin coating, it's the lowest cost of all these things, of all the ones we're going to talk about. It's pretty simple, and it's a pretty fast process too. The main thing though is that your material has to be in some sort of liquid state when you get it, liquid or a resin of some sort, where it's not too viscous and it's not solid. And so what I have there on the right is a picture of what a spin coater looks like. It's just a cylindrical box where they seem to have a 6-inch wafer already put in there. Hook it up to the chuck, turn on the vacuum so it's sealed on there, and then you set all your parameters. Things like how fast is it going to accelerate? How much time is it going to spin for? And the most important one, what speed? What's the max speed going to be? So things like the acceleration and the time that you're going to speed it up for speed up whatever this process is. Um, or the you want to make sure you know what viscosity this is, and by that I just mean, is it a very viscous material or is it not a very viscous material? If it's a very viscous material, then you should probably spin it for a little bit longer, right? So that way the material can spread out. Because how this works is that you're going to pour the material onto the wafer, and it's going to sit there, and then as it spins, right, we're going to use the centripetal force of the scenario, right? Because that material is going to be in a spinning frame. So I guess it would be centrifugal in its own frame, and it's going to slowly pull the material out, and it leads to a very uniform film, usually. Um, Now, usually, if you're using a photoresist that is very ubiquitous around industry and in many universities, kind of like this Enloft 2020 spin curve I have right here, I got this straight from the data sheet. Then you should be able to follow the data sheet and say, okay, I'm going to spin it for 2,000 RPM for like 30 seconds or a minute or something like that, and I should get just over 2 micron thick film. If you're working with especially a novel material or material you don't know, this is where one of the biggest things I always tell people, always make sure you have extra samples. So that way then you can test out a couple things, maybe 3 or 4 times on small samples, and then look at what the film thickness is using some profilometer. Because when you have the film thickness and you know how much you spun it at, you can make your own uh, spin curve. So always make sure you either have a spin curve, a known spin recipe, or you make one. So next is PECVD. It's a little bit more complicated. So in this case, was it this specific slide? We're going to focus a little bit more on plasma enhanced CVD, but the main idea is still the same. In normal CVD, you're going to pump out. Okay, you're going to put your substrate in this chamber. It's going to pump out, put you in vacuum, put your substrate in vacuum, and then it's going to pump in some precursor gases. And the reason why you do that is because then you inject the gas you actually want to see some of the material with, and that injected gas will interact with the precursor gas, leading to, if we ran through all the stoichiometry, whatever it is, it'll lead to a solid material that will then deposit on your substrate. The thing about PECVD is that instead of using one of those gases, it uses a injection gas that reacts with a plasma instead. And interestingly enough, because of that, it has a lower operation temperature, which then expands the range of materials that you can then use. And so that's where this is mainly used for a lot of glasses. This can be used for some of the other photonic materials we didn't talk too much about. So like your silicon nitrides, your silicon carbides, things like that. And the plasma enhanced version also has faster deposition rates than a common CVD. There are a couple organic materials that can be put on there, but those are pretty few. So you'd have to look up to see if you could do that. Yeah, there are several other versions of this sort of process. Some that are used to deposit some metals and things like that, but for the most part, PECVD is pretty widely used. So all the other different variations you'd have to look up to see which ones suit your needs. And then the last one overarching topic we're going to talk about today is sputtering. Now, sputtering, just like CVD, has a lot of different ways in which you can do it, but it's a much more physical process than those. It deposits using a much more physical process. So one way you could do it is that usually what happens is that you're going to have your target material, and it's going to be in some sort of ingot. Sometimes it's a cylinder, sometimes it's just like a bar. Point is that it's going to be sitting in your chamber, in your vacuum chamber. And then what's going to happen is several different things can happen. One of them is that it's heated up to high heat, which will then expel atoms from this material or molecules, depending on what it is. Or what it can happen is that, and this is the one, if I remember right, we have at the U of A, where it uses an electron beam that will very physically and very violently strike the sputtering target, which will then cause material to fly towards your substrate. And by substrate, I just mean your sample, whatever you're trying to deposit on. Some examples use magnetrons. Some examples use high intensity lasers. Others use straight up ion beams. The example I have here in this diagram uses specifically argon as a sputtering gas, which argon, since it won't react with your, it's a noble gas and it shouldn't react with your sputtering target, and it's a largish atom, and so it will physically strike the sputtering target. This is mainly good to use in some electrodes and contacts and electrical contacts. That would be for those phase shifters that we've talked about. And so that's been the main example I've personally seen is it being used for those applications in metals, particularly. You can use it for certain other things. I have seen it used for the thin film lithium niobate. It has been used for things like that. What is it? Okay. Now then, that was a lot of stuff all at once. So now let's go and do our first Zoom poll question. So, setting the scene, you're testing a polymer platform for photonic waveguide architecture, such as some waveguides, and it's delivered to you in some sort of liquid solvent. How should you deposit this, or how might you deposit this? Seems like seems like A got most of the answers, and that A would be the correct idea. Was it PECVD, right? Is where we have plasma with some sort of injection gas. There's some chemistry that happens, turns into a solid. Sputtering is where you start with a solid and then you sputter it using some sort of physical process. Um, Dip coating is something we didn't talk about, and that is just real quick. That's the whole idea that you could do that with a liquid, but dip coating is exactly as it sounds, where you take the sample and it dips into the whatever this whatever this compound is, and you just slowly pull it out and let it drip off. That's okay for some processes, although it can lead to non-uniform films if you're trying to get down to the specifications and the types of architectures and the types of resolutions that a lot of our applications need. You should probably spin coat instead. Alrighty, now then. So now you've deposited the film. How are you going to pattern it, right? So now we're kind of to that third step in that original diagram. This kind of covers this photolithography slide basically just outlines that whole diagram that we saw at the beginning. So the whole idea is that you are now going to expose it using some sort of UV exposure. So you need to be conscientious of which photoresist you used. So you've put on your material and then you put a photoresist layer on top. Which photoresist you use will decide how much dosage you should have. And dosage measured in millijoules per centimeter squared, it's essentially an idea of power, is how intense of a beam are you going to illuminate the photoresist with? Because if you don't illuminate it enough, you won't have that chemistry happen inside of the photoresist. It won't develop right. And then when you go to your etch, the whole architecture is wrong. So yeah. And so then after that dosage happens, then then you take the sample out, you find whatever the correct developer is for that photoresist, because that developer is designed and works specifically with that photoresist when it's illuminated or not. So it depends on which one, whether or not you chose a positive or negative photoresist, will decide whether or not the developer will take off the exposed regions or take off the non-exposed regions. So you need to be careful of that too. I've had it once or twice where I've made the design, ran through the whole thing, and then realized instead of making a waveguide, I made a trench, and that's not good. And then moving on from there, that's where we do etching and cladding. So we'll talk about etching later. Another common technique is E-beam lithography. So it's a very similar process, and so that's where on this slide I'll talk more about how it's different than photolithography. So first of all, you're going to put on what's called an E-beam resist instead of a photoresist, and it's for the reason that you're going to be using an electron beam to do similar chemistry, not the exact same processes, but as the photolithography photoresists resists. And why this is beneficial is that the big E-beam tools that people have made have been able to get very high resolutions. From the numbers I've heard is resolutions on the order of 10 nanometers versus 100 nanometers with photolithography. So if you're working with something like SOI, where you can make very tight bends, you might want to use e-beam lithography for that. So yeah. The problem though is lower scalability. And this is one of the big issues when it comes to anything to do with photonics is always, things like cost, just like anything else you're engineering, but also scalability. How many things can I make? And how fast does it take to make them? So e-beam lithography takes a very long time to do. So if you're trying to make a very long, very large structure, something like a maskless photolithography, the stage usually is allowed to move. The right head that illuminates the photoresist is usually able to move pretty far. With e-beam lithography, you get that resolution. However, it does a very small area and then it has to move over and do this very small area and moves over, and it takes a very long time in order to do that. Um, there was a design I've done that took me about 5 minutes on 5 minutes doing photolithography. It took me over an hour and a half with e-beam. It was almost the exact same design. So these are things you want to think about, especially if you're trying to make a very long and very complicated and a structure that takes up a lot of real estate on your wafer. So these are things to think about. Okay, and then with that, all right. This is a question that's kind of harkening back several slides ago. But if you're trying to change the phase information of a photon with a thin film lithium niobate, what should you do? Should you A, deposit an ohmic heater on there in order to change the index by changing the temperature? B, should you deposit an electrode or electrodes, I should say, over a desired region and apply an external field to it? Or C, should you find another laser pump and then pump it in a region but in another direction? Already, we have a little bit of an even spread here. So when it comes to A, was it thin film lithium niobate does have some uh, some thermo-optic properties. I mean, almost pretty much every material does. Um, However, thin film lithium niobate has a very strong Chi2. Uh, and so because of that, we can, by putting just one electrode across it, not periodically pulling it, um, we should be able to apply an external electric field onto it and then should be able to change the phase information. So this would be the answer for this one would be B, right? Ready? Now then, so this is where, going back to photolithography before we move on, you're going to hear the term photomask a good bit when you work with these technologies. And so the whole idea of a photomask is that it's kind of like what it says. It's a trace of the design that you want that you'll put over your photoresist. And so e-beam lithography, that's one of the benefits is that it doesn't need a photomask. Photolithography, a lot of the times, or depending on your application, it can. So to make a mask, it's awfully time consuming. Sometimes people use e-beam lithography to make the mask for photolithography. So that should tell you it's a bit more pricey to make one. Most of the time, the idea though is that you have some sort of opaque material that will stop the UV. That's what I have in the black bars there in that layer. And then you have some sort of transparent material, maybe SiO2 or something like that, that allows the UV to go through and illuminate the pattern. Um, that is compared to maskless, where maskless is like I have here, that thin pink arrow. Maskless is simply we're gonna take this beam or this UV exposure, and instead of making it as big as a lamp, like a big UV exposure system, that will just send photons down, do the interactions, yada yada. Instead, it will take this laser and move it down to a small right head, and then it will slowly write across the surface. All right.
I just want to
Um,
interrupt really quickly.
yes.
Um, SiO2 absorbs a
Mhm.
lot in the UV. It doesn't transmit, I'm pretty sure. So
Oh,
you need a different
right.
material there. But yeah,
It is a different material.
yeah,
I said transparent. My mind went to SiO2. SiO2 is transparent in IR, not UV. Wrong
yes,
way.
yeah,
Yeah. No,
no problem.
you're right. My bad. Yeah. Um, Yeah. Okay. Yeah. But so this would be the difference between mask versus maskless. So when you're thinking about what resolution you want, having a photo mask usually can give you a slightly better resolution. Um, and so if you have the photo mask on hand, that might it might be worth doing that. That is yet again, it all goes back to what materials are you using, what photoresist, so on and so forth. Okay. Speaking of which, let's see here. Zoom pole 8. If you're making interconnects between two integrated circuits, so that's just what's connecting two circuits. And assuming that these interconnects are just straight waveguides, so they are, and you do not have the proper photo mask that you want. Okay, so you don't have the photo mask on hand. What is the proper lithography technique? Um, and that minimizes the time, minimizes the costs. Would you spend the time to create the photo mask and then use photolithography? Would you use e-beam? Or would you use a maskless lithography process? Already. So it looks like most of us says use the maskless lithography process. Yep, that's a good that would be what I would say, and that's why I made sure to put in that minimizes time and costs. Because all three of these processes could do this. And they could do this very well. But and this is a especially because this is a straight waveguide, all three are very capable of this. Um, but if you don't have the photo mask on hand, well, now your choices are just maskless lithography or e-beam. And e-beam takes a good amount of time. Uh, when it comes to clean room costs, it costs a good bit. We're not going to talk too much about the economics of it all, but it's just e-beam costs more. So you might as well just do the maskless lithography process. So if you find yourself in a pinch, go with maskless lithography, depending on your architecture, of course. Okay, now then, you've done the photolithography. You've developed it. Now you just need to etch away the part of the film of your target material that you don't want. So what etching essentially does is exactly that. It looks at those holes in the photoresist and it starts etching away the film underneath. So there's two different types. The main one, and this is the one that I've done pretty much exclusively, is dry etching. And one of the common types is called RIE or reactive ion etching. So the whole idea is that another vacuum chamber, another large piece of equipment, you put your substrate in there, and then the chamber is filled with some sort of gas that will create some free radicals. A very common gas that's used is CHF3, and so F3, anything with fluorine, right? Fluorine wants to grab onto things, and so there'll be a little bit of chemistry going on that's going to start taking away parts of the film. Um, another gas that's used a lot is argon, and it uses just about the same idea as the as in sputtering, where argon is physically striking your film, and so it's etching it away. And so there's pretty good selectivity, right? Because uh, some of these free radical species are going to interact with the photoresist differently than the film, so they have different etch rates. And keep in mind, these etch rates, it's linear, all right? So when you're modeling etch rates, that should be pretty quick. It should be just a straight line when you've done all your test data. Um, and there's a fairly good selectivity, like I said, with these species if you have a good recipe, and when you're making a good recipe, that's what you want. But it does still etch away the photoresist with the film. So you need to be careful of that. You want to make sure that the film will etch away completely. Let's say you're making a channel waveguide, so you want no ridge, no rib. Then you want that film to etch away completely before the photoresist etches away. So you have to be cognizant of that. What your thicknesses are and what their etch rates are going to be and how long you're going to etch, because they're both going to etch at the same time. Moving on to wet etching, it's just as you might imagine, there's a liquid etchant that you use instead. So it's a vat or some container of liquid, and then you take your sample and you pretty much dip it in there, and it will slowly, it'll have some sort of volatile compound, especially to whatever you're using, and it will just start to etch away at the film. The problem, and it has very high selectivity also, so that's good. So that means your photoresist layer may not be touched almost at all. It probably will be etched away a little bit, depending, but not that much. The problem is, if you look at the diagram up there, is that think about it, it's a liquid, so it's going to go into the hole and etch straight down into the hole, but it's a liquid, so it's going to be resting in there and it's going to start etching into whatever your structure is. So that's going to create a problem. And that's where that minimum feature, was it this diagram saying about 2 microns? I think the number I think you should pull away from that is about on the magnitude of a micron or 2 microns. So you want to be careful with that because then that means you can only make your waveguides so wide or so thin. I mean, so that's something you got to think about. The benefit to wet etching then, right? Because if it's going to mess up my architecture, what's the point? If it's going to mess up the shapes and the dimensions, what's the point? The thing that helps is that it has a large throughput. I can have a large container of this stuff and I can put, 3 to 5 6-inch wafers in there, or three or yeah, 6-inch wafers in there, and it'll etch all of them all at once. Versus in dry etching, I can only ever every machine I've ever seen can only fit one wafer at a time. So it'll take a lot longer. And especially when it comes to dry etching, if you need to use something like a cryo etch, so now you're using up a lot of liquid nitrogen. That's a whole nother concept, but yeah. So with all this established, we're past this etching step. Which lithography process would I probably want to do if I want to make that photonic crystal like we were talking about before with the small nanopillars, right? Would I use maskless photolithography? Would I use e-beam lithography? Which one do we think? All right. Looks like most of us use e-beam lithography. Um, I wouldn't deny if there are examples of someone using oh, if someone used like a photo mask with photolithography, I could see that being used maybe in some applications. But if it's maskless versus e-beam, no. Mainly because those nano pillars, especially if they're cylindrical, the dimensions I've seen on those are usually on the order of 10 nanometers, sometimes 50 or 60. But yeah, they're definitely less, and especially if the shape of those pillars is very important, whether or not they're square, whether or not they're hexagonal, rectangular, or if they're uh, or if they're cylindrical. That makes a very big difference. So so from there, after you etch, right, you just put on your top cladding. That can be done in several different ways. I mean, you could try to put an SiO2 layer on top. You could try to spin coat on some sort of resin. That's something that I've done, things like that. But once you have that cladding on there, you're pretty much you have your device made. So now the next question, what devices am I going to make? So the first thing you want to make is, okay, how do I turn a signal from one waveguide into two? So we got 3 different ways to do that. We have a Y branch, and what that is basically exactly like it sounds. It makes the letter Y. So it's pretty much one waveguide comes in and then it splits into two. All right. The key there is symmetry. If you want a 50-50 splitter, it has to be symmetric on both sides. So where that Y branch splits, and especially that vertex, that corner, is very important. The next one after that, multi-mode, it's a multi-mode interference coupler, or an MMI. So what this uses is that you have one waveguide coming in, and then it connects to a larger rectangular region, which is kind of like almost a free propagation region is kind of the idea. And then at very specific heights at the other end, you have two waveguides coming out. And so from it all works with the same boundary conditions and the same math and everything like that. But because that rectangular region is so wide, there will be certain solutions on the other end to where your two waveguides need to be, to where it'll actually couple into those two waveguides at the wavelength you want. Something to pay attention to because this is was it if you look at the pattern there, it kind of reminds you of kind of the classical diffraction type of examples. But because of that, it is very wavelength dependent, and you have to optimize the height and width of that rectangular region for that whatever wavelength you're targeting. So you got to be careful of that. One last side note is uh, you can use an MMI at the base of a Y splitter, and then after it splits into two waveguides, the rest of the Y splitter is just these S bends, if you will, that just pull the waveguides away from each other. And the reason why we want these waveguides to pull away from each other and be far enough apart from each other is because we don't want what's called, sometimes you don't want what's called evanescent coupling. So evanescent coupling is this kind of is this idea of the mode profiles pretty much being, or what was it called? If we remember in Shelby's part earlier, she had those diagrams with the mode profiles, and you guys could see that there were the little tails that were trailing off on each side of the boundaries from the waveguide. Now, sometimes those go off a significant amount, and if you bring another waveguide close, very close to your first waveguide, that tail can couple and can couple into the second waveguide, and essentially power can be coupled and leached off of the first. And so what that means is that when you bring two waveguides together, power starts moving from one to the other, and the longer you keep them together, more power leaches over. And that's where when you have this region, you need to optimize what that length is if you want a 50-50 splitter. Because if you think about it, if they keep going, all the power leaches from waveguide 1 to waveguide 2, and now waveguide 2 has all the power. So if the region's longer, then the power goes back. And so it can bounce back and forth for a long time, or you need to make sure from all your parameters, things like, your effective index, how much coupling is going on and stuff like that, how far away your waveguides are, you would need to optimize what that coupling length is. So that way, only 50% of the light goes over to waveguide 2, and then they go away from each other again. So these are things to think about. All right. So then for our next idea, okay, I can split it up 50-50 in all those ways. And with this device, even though I'm using Y splitters as an example in that diagram, and you can use all three of them. You can make what's called a Mach-Zehnder interferometer. If you think back to, if you have any, if you remember some examples with some classical optics, right? A Mach-Zehnder interferometer is essentially photon comes in, and then there's two paths it can go down, either sometimes symmetric, sometimes not. In this case, there's a short path and a long path. And then whatever photon, whichever path it goes into, it recombines. Both of the paths recombine, I should say, at the end. And so from this, you can have a signal where part of it goes down the short paths, part of it goes down the long path, and then you can manipulate how asymmetric it is. Maybe you designed it to where one side, like I have here, is a long path, so it's way longer. And then that changes how much the phase information of the outgoing photon. And so from this, you can modulate the intensity of your signal. If we look, I have this gold or yellow arch right here. That is some sort of phase shifter. So that's either your electrode if you're working with second order, or it's your ohmic heater if you're working with third order materials. And so with that, you can change the intensity of the signal coming out, or if you're trying not to tweak it and you're just trying to kill it entirely, then you can make an optical switch. So you can turn this whole MZI on or off, essentially. Another thing you can do is you can use it to help filter out certain wavelengths, right? Because different wavelengths, remember dispersion, different wavelengths are going to move at different rates and have different phase information at the end of this MZI. And so with that, this MZI then has what's called a free spectral range, in that if we took a very wide spectra, looking at all these different wavelengths that go into the MZI, only certain ones go through. And so with that, we can use this for some selectivity, and especially when it comes to our very discrete pump signal idler photons, that becomes very important. And lastly, like I said, what's it called? I've talked a lot about how there's a short path and a long path. With that, you can then try to then path encode a qubit onto this. I've seen a paper before where instead of using 0 and 1, they actually assigned the kets for each state as S and L, as short and long path. So poll question 10. After we place a top cladding, and it's placed on top of a PIC, you want to place an electrode for a phase modulator on one branch of the MZI, kind of like what we saw before. You've already deposited the photoresist for all that, so you already have the pattern on there. You just need to put the material on it. And you have it in the desired dimensions, right? What would be a good process that you should use, or maybe is a good idea to use, in order to get these electrodes on there? And remember, these electrodes are most likely going to be metal, right? Alrighty. So we had a good amount of people say PECVD, and C, we had a good amount of people say sputtering. Um, Most of the time when it comes to metals, I would suggest sputtering. PECVD, that is not usually the one that you would use for metals. There are some CVD processes where you do deposit metals, but most of the time sputtering is what you would want to use. When it comes to spin coating the molten wafer, that or molten metal over the wafer, that has in order you'd have to heat up the metal however much that is, and that would create some sort of breakdown, some sort of dielectric breakdown, depending on what your materials are, and that can create problems. Um, so, because some of these materials, even when they work at room temperature, are still very they still have problems working in extreme heats and extreme colds. So that's why you wouldn't want to spin coat on the metal. Um, Alrighty, now the last type of thing that we're going to talk about. Now there's this one, the theory behind it gets very complicated. There's an entire textbook just about designing these things. But it's what's called a ring resonator. And the diagram, I know it looks like an oval. I'll give you a reason for why that is in a second. But with the ring resonator, you have what it essentially is we use that evanescent coupling, the exact same way we did with the directional coupler in from what is called a bus waveguide or a source waveguide, pump waveguide, stuff like that. And then we have usually a circular ring on top. And so at that region, some of that light's going to go in and it's going to go around. And so what you want to do is you want to optimize this ring and the properties thereof around what's called the critical coupling condition, where it's essentially saying this is the condition where light doesn't recouple back into the bus waveguide, where there's an equivalence, if you will, between the amount of power coupled into the waveguide and the amount of power lost from bending losses, absorption, scattering from one round trip around the waveguide. And so when you play around, get close to this critical coupling, maybe you make that L sub gap. So you make the gap length a little bit smaller, a little bit bigger, play around with that. So that way you can get that pump waveguide into the resonator and it starts going and it stays there. Because if it stays there, then you have a device with a very small footprint, but has a very massive propagation distance for your pump photons. Then you can generate your EPR pairs that much easier. So it's a pretty powerful technology in that way. Um, an alternative to that would be like a spiral waveguide, which we're not covering, but that idea is just a very big circle. That's just a very big spiral. It works just the same. It's just that there's a lot of it takes up a lot of space on your wafer. So if you're trying to scale it down smaller, that'd be a problem. Um, the two main things we want to get out of these ring resonators, we want to maximize the Q factor. So what that's telling you, if we took the spectra of what's coming out of this ring resonator, is you'll look at the resonance, you'll see a resonance peak, because that's where that wavelength was taken into the ring resonator. You're going to take the frequency of that resonance peak and divide it by the full width half maximum of that peak. And so that tells you a good bit about what wavelengths you can resolve. And that's a very big deal when it comes to resolving your pump versus your signal and your idler. Depending on how many signal and idler pairs you're making, it could go very far away from your pump. But depending on the material, sometimes they're very close in wavelength. And I know it's very relative terms, but they can be very close. And if you don't have a small enough full width half maximum at the pump, you'll have problems resolving. You'll have problems resolving the what's it called? The signal and idler photons. Then the other quantity you want to pay attention to is the finesse. And so that's where that F, it's usually denoted with a script F, if I remember right. And so what the finesse is that it looks at that free spectral range that we saw before. So essentially, how far away are the resonances in this ring? And it looks at the ratio between how far they are away from each other, and it's full width half maximum again. And so that kind of tells you how well you can resolve each resonance. And so yeah, and so because of that, when you want to maximize the Q factor, maximize the finesse, you want to tweak all of these geometric dimensions. So you want to tweak what is the radius of curvature on this thing? Because the tighter the radius of curvature, the more bend losses you're going to have. What is the length of the gap? The closer they are together, the more light that's going to couple in. And what's the length of your coupler? So of the coupling region. So how long is it going to be coupling into uh, into the ring? And so when you change that coupling length, that's how you get what's called this racetrack design. Sometimes there's pulley waveguides where it's the same idea. It's called a pulley waveguide because it looks like a pulley, where you have the ring and then the waveguide goes around it like that. Same idea. It just bends itself. What is it? All right. Going on to, I think this is our second to last question here. So, what exactly makes ring resonators good candidates for nonlinear EPR pair sources? All right. So most of us said A. That's something that I would agree with. Was it B? It's so whether or not it's second or third order depends on what your chosen platform is. So if you choose something like thin film lithium niobate, then you're going to be relying on some second order types of stuff. Uh, but remember that that's also spurred on by some external help too. So when you do second order processes, you will get larger intensities than third order processes. This is true. It's just that was it the material? There's all the other cost sorts of things that we had talked about. Um, oh, how do I put this? How do I put this? But also, you do need the biggest thing to remember with second order sources is that they also have third orders. So you can have many materials that are what's called well, you have many materials that don't have second order effects, but they do have third order effects. But pretty much every material that has second order effects has third order effects. And so that becomes a bit of a problem. Because then as you guys saw before, I had the electrode on top of that ring resonator. Then you would need to do a little bit more in order to negate those things. Because now when you're applying that electric field, you also need to consider how much temperature does it change. It doesn't mean that second order materials are necessarily bad materials or anything like that, but it means that there's extra things that you need to look into. And so what the point of what I'm saying is that the ring resonator itself is a good candidate, and it's a good candidate for both second and third. It just depends on how much are you willing to put into it, really. Um, yeah. So from that, we have these three ideas. We have our couplers. We have ways to split information into two different waveguides. We have ways to filter them. We have ways to generate EPR pairs. So what do we do when we have a full system? So this is a diagram, or this is a diagram from one of the company's PsiQuantum's papers. And so what it's essentially doing here is that it's making the heralded photon source. So it's using the ring resonator to generate the EPR pairs. I know it says heralded sources, but it generates the EPR pairs, which are then heralded. Um, then what we see in yellow there, that is a filter system, which is a lot of several MZIs and several rings that are used to filter out the pump. And so from there, then you get your heralded photons that go down to the state preparation stage, where then they are these further MZIs, which, as you can see, they're not using Y splitters here; they're using directional couplers. So it's kind of a two by two directional couplers. These MZIs are then optimized to path encode the heralded photons, and then over there at the end, they are then measured. And so there are uh, many different ways you can expand from this. For instance, you can what is it called? What they do after this in that exact same paper is that they prepare the state, they path encode it, then they move it down to they move the waveguides down to the end of the chip where there is what is called a fiber coupler on there. And it's a different device. We haven't talked about it here, but it's essentially a way for you to put a fiber onto a chip and then get the information out. And so from there, they're able to go from chip to a different chip and then measure on a different chip. They're also able to expand it. Okay, well, instead of making one photon source with what if I made two? And so then they were able to make two single qubit states and then interact them with each other and things like that. So from these basic passive devices, we're then able to what am I trying to say? We're then able to uh, filter, design, and encode our qubits, and from there we can then start doing more system oriented and make larger, more complicated systems. So, and then this is the last one here. We're going to end it off with just one more question. So, you have a ring resonator uh, made from a material with a high third order nonlinearity and no second order nonlinearity. Okay, so this is kind of answering for some of you folks from the last question, right? What happens when I have just a third order material? Um, and the bus waveguide has already been optimized to the pump wavelength, so you don't really want to change that, because if you change that bus waveguide, the waveguide at the bottom where the pump's coming in, that's going to increase the loss. So what should you do to maximize the Q factor without fabricating a whole new device? Alrighty. So some of us said place some electrodes on some region of the ring and apply an external field. Now remember, when I'm saying electrodes, I mean we're going to put a potential difference across this waveguide and apply this electric field. Remember, there is no second order nonlinearity, so the crystal won't. So there's not. It's not a. Assumedly not like a ordered crystal like a lithium niobate is. So that would create a problem. They wouldn't do too much. Some of you guys who said B, this is what I would say is deposit a titanium gold layer and use it as an ohmic heater. That's a common thing that's used a lot. Sometimes it's aluminum, sometimes it's gold. But yeah, so use it as an ohmic heater. Take advantage of the thermal optic coefficient. Because if I can't apply an electric field to this waveguide in order to change its properties, well, then I should probably change it using heat. And depending on what material you use, it always goes back to that. Depending on what material you use, that thermal optic coefficient will either be very large, so it would change a lot, or it won't change a lot. So it depends. C is an interesting idea. Place the entire device, so your whole ring resonator, on a Peltier device and heat it up, the ring and the bus waveguide. Heat up the whole wafer. Why not? Well, the main thing though is that your bus waveguide is as established in the question, is already optimized. You don't want to change that. All right. And the last one, D, apply a strain to the resonator. So that would be kind of, you apply some sort of nano force on the sides of the wafer and try to stretch it just a little bit to where it's under some sort of strain. Um, that could be a problem depending on what materials you have and the adhesion. And it'd also be very difficult to control that type of force, that type of very small force you'd have to apply. So I wouldn't do that one either. So B would be the best one here. Alrighty. And so from here, we start talking about foundries. Was it Shelby? Did you want to take over here?
Yeah. Um, yeah, so we just wanted to end on like a much larger note. Everything that Wyatt has been talking about and everything that I've been talking about has been so far on a pretty uh, prototype basis, going in, trying to figure out the specifics of devices that you want to fabricate, testing them on a small scale. But once you get something that you want to work, one of the big reasons that we talk about integrated devices for quantum networks is the idea of scalability, of making